I can remember how to do this. It's been so long. All right, so I want you to tell me how to do a couple things here. This is, you can come up with all these answers yourself. I'll just kind of put some stuff up here and you tell me how it works. The situation we've got going here is, this is the, oops, that's what I want right there. This is the VT plane, so we're graphing velocity versus time. We've already talked a little bit about this. So what does that area or that curve represent right there? So I guess what I really, maybe I should do this. This might make it just a little bit clearer. What if we put, well, yeah, it's a curve. It's not a very exciting one, right? But it is a curve. Let's make this top one. So here's the function, and we're looking for the, potentially the area under that curve. But that's the graph. So explain that story to me. What's going on there with that particular graph? Velocity's not changing. It's constant velocity. Let's assume that we're measuring in standard units, meters and seconds. What's going on? So what's happening there? It's a pretty boring trip that's being taken.
Yeah.
But what's happening?
You're on cruise control.
And how fast am I going?
The area.
Going 6 meters per second. For how long?
8 seconds.
How far do I travel then? If I'm going 6 meters per second. How
48.
40? How'd you get that? Yeah, because that's we know that speed is just, or distance equals speed times time, doesn't it? Right, rate times time. Okay.
Wait, how did you get this speed?
I just counted. 1, 2, 3, 4, 5, 6. Right, 'cause we're just going in standard increments, meters and seconds. Okay, so how else geometrically could you get that displacement? Yeah, you could also just calculate an area, couldn't you?
Yeah.
Okay. Now, and it's been a while ago, but we mentioned that. We talked about kinematics a long time ago, but that's one of the nice things about when you study kinematics and you look at kinematics graphically, the area under a VT graph is equal to displacement, right? Okay. So now let's add something to this picture. So we've traveled here, in this case, 48 meters, right? Because does that make sense?
Yeah.
Okay. All right, so what happens though if we add another piece to this story here? Let's say that this is actually, now we're going to bounce off a highly elastic wall. And what happens here?
Well, you can't go negative.
You go backwards.
Oh yeah, it's just backwards, exactly. There we go. So now we're looking at the area under that curve. Okay. And by area under, define that more precisely for me. We talk about area under a curve.
What's the relation between the...
Go ahead, between,
and the x-axis?
okay, between the x-axis, or in this case the t-axis, and the curve, right? So it doesn't mean, under doesn't mean down, right? In this case, down, if we went down, we would, whoops, that's not down, is it? If we went down, we would just go,
Too high.
and forever, there's nothing to stop it, right? We just mean area between the axis, independent variable axis, and the curve. And so, what is this one telling us we're doing? Yeah, right? This time we're going negative 6 meters per second, and that just means 6 meters per second in the opposite direction, in the negative direction. Once again, for 8 seconds, right? So how far do we travel here? Yeah, here we're just traveling negative 48 meters. And so what should my net displacement be?
0.
Hey, this is for you. Here's let me give that to you. Oh, it should be 0. It should be 0. Then what does that tell us? And we, once again, we talked about this prior to spring break, but what does that tell us about area underneath the x-axis or the t-axis in this case? How do we reckon that area? we talked about area, didn't we, about adding going, didn't we talk about when we added up in the opposite direction and things?
Yeah, I think so.
Okay, so let's quick review that. Quick review. So when we're adding up area under a curve, and I can't, we didn't spend a lot of time on this though, so this is something we need to talk more about anyway. If we're adding up area under the curve F from A to B, that's positive area, isn't it? Right? So we would say then, if the area under that curve is, let's just say hypothetically that it's 10, then how do we write that with an integral?
Yeah, integral from B, and B's on top.
Okay, from A to B, right, that's how we say what we call the limits of integration. That just means that, we're defining the lower and upper boundary of the area, okay? What goes here?
C.
F of X, right?
Oh,
Because that's, and what's that doing? That's just telling us what's the top boundary of the area, right? What's the function under which we are adding up area, right?
Yeah.
Then dx at the end, because we always put the integrand between the integral sign and the dx, right? 'Cause- and really, how come it looks like this? Because of that weird, handy relationship between definite integrals and antiderivatives that we uncovered, right? That's the trick, the first fundamental theorem, which allows us to do these problems so much more easily now than having to go through the whole limit of a discrete sum, right? I mean, that was getting old. But now we can do this instead. Okay, but all this means is area under this function starting at x equals a and ending at x equals b, right? Okay, it's been a little while, the spring break kind of sometimes spring break, I don't know what happens, it's like a brain drain
Yeah,
a little bit.
exactly.
So if we wanted to add up the area under the curve y equals x squared from 0 to 2, do that for me real quick. How would we do that? Integral? What's the, oh, actually, this is an x squared. Sorry, this is, this function right here is 4 minus x squared. So what do we get?
Oh,
Say it again? Well, we'll just go from here. We'll just add up this area right there.
Oh, okay.
0 to 2,
4 minus 6 squared.
4 minus x squared. I need parentheses around that, don't I?
Yeah. And dx. Yeah.
Okay. Now, let's do this integral, a little practice. What's the answer?
Antiderivative.
Yeah, what's the antiderivative of 4? 4x.
Minus 6 squared over 3.
Ah, good, okay, minus x cubed over 3, and we're gonna evaluate that from
Or 0 to
0 to 2, right? Remember what that means? We're just gonna evaluate this expression at 2, subtract from that the value of this expression at 0. Well, what is the value of this expression at 0?
0.
0, that's handy, isn't it? So we just end up then, in this case, with, let's see, we're gonna get 4 times 2 minus 2 cubed over 3 minus 0. So that's just 8 minus 8 thirds, so 16 thirds. So that's our area there, isn't it? Right?
2.
From 0 to 2, so if we added up this area right here, this area in blue, right? Okay, but what did we say about, what happens if we add the area up in reverse direction? Becomes negative, doesn't it, right?
Yeah.
Right, okay, so that's one thing that happens. If we add up, the way that we reckon area normally, positive area is reckoned from left to right above the x-axis. Now, if we reverse the direction, that makes the area negative, okay? Or the other thing that could have happened is, if the function drops below the x-axis, then that's negative area, right? And the example we're looking at right here is like that. If we add up this area, why is it negative? Well, it makes sense because the value of v is -6 times +8, right? Does that make sense? Now, what about can somebody make sense of the adding up area in reverse order thing, maybe? Why, if I started here at t equals, this is t-axis, right? At t equals 8 seconds, and I went backwards to 0, why would it make this green area -48? Think about it, it makes perfect sense.
Because you're taking the smaller number to check the bigger.
Okay, mathematically, physically, why would it be that way? Because the area under the curve represents displacement. Yeah, it's like running the movie backwards, isn't it? Instead of, here's the movie going forwards, I'm just going forwards at 6 meters per second for 8 seconds. Now, if I stop the camera and roll it backwards, I can't talk backwards, but I would just end up right here, wouldn't I? The displacement would have been, I started out there and ended up back here. So it would have been a negative displacement then, right? All makes sense, doesn't it? Okay. So what's going to be the displacement of this story after 16 seconds? You already told me, I think. If I add all that area up, what do I get?
0.
0, yeah. I should end up right where I started, because I'm going forward, I bounce off the wall, and I come back to where I started, and I haven't gone anywhere, right? Okay. That's displacement, or sometimes, physics, we'd say displacement. And that's the word I definitely prefer, displacement, but you can think of that in a way as being net area. Okay, in terms of just the calculus, it's net area, isn't it? Because that counts as, what does net mean versus total or gross? Like if you're talking about your net income. Yeah, it's like after you've had some income and some expenses, right? Taxes, etc. So it's what's left over. It's when you account for all the negative contributions also, positive and negative contributions. What do you end up with, right? So a net area in this case is 0. Now, what if I want to know instead, though? Here's another question. What if I want to know what's the total distance I've walked? And that's different than displacement, isn't it?
That'd be 96.
96. How'd you get that?
Just added them up.
Added them up. Okay. So then what's the calculus recipe for calculating the total distance that's traveled? And that's important, isn't it? Because if we wanted to know, now the average velocity for this trip was 0, right? Average velocity is just displacement over time. But if we want to know the average speed, it was not 0, was it? Because I was moving. What was the average speed? Yeah, it was just 6 meters per second, right? Makes sense? Because speed is always positive. Speed is a scalar quantity, it's always positive. In a car, we have a speedometer. It would not be very useful to have a velocitometer in a car. That would be, because if you turn, that wouldn't make any sense, right? As you went backwards, it would turn negative, and it'd be strange. We have a speedometer, and if we were walking with a speedometer here, it would never have changed, right? And so if I want to calculate the average speed, for example, I would need to know the distance traveled. How am I going to get distance? In general, then. Go ahead.
Just add them both up.
Yeah, so how would I always ensure that my contributions were positive?
Absolute value.
Absolute value, yeah. So I'm always taking the absolute value of the area, right? Does that make sense? Okay. So distance equals total area. In this case, with a velocity time graph. Okay. Now, if I just do, this is kind of a subtle point, but I want you to see this. If I just did, you tell me what's wrong with this picture. Distance equals the absolute value of the integral of f of t dt from 0 to 16. This just stands for the area under the curve from 0 to 16, right? What is that, by the way? Say it again. What is the area under the curve from 0 to 16? No? 0. So this is just saying the absolute value of 0. You have to take it separately, don't you? You have to add up all the contributions of the areas separately. And by separately, what do we really mean there? Say it again. They would be different terms. You'd be adding up separate terms. And what's going to separate the term? In this case, how many different terms would we have? 2. How come? We'd have to add up the green, absolute value of the green separate from the absolute value of the yellow, wouldn't we? If we made the terms, well, what if I broke the terms right here? That's not going to work, is it? If I add up 2 terms, one of them goes from 0 up to 12, right? So I break it into 2 pieces. So I'm adding up that area first, and then the second term would be from 12 to 16. It's not going to work because look what's going to happen. This part right here is going to cancel that part right there, and I'm going to get a small contribution and then another small positive contribution, right? Are you getting the subtle point I'm making here? That I have to add it up in 2 terms because there's 2 areas, but there's something else, and maybe it's just so obvious that you're not saying it, but there's something else I also have to do. Where do I always have to separate the terms? Give you another example. What if this is our function? I want to add up the total area there. Okay, how many terms am I going to have? 3. Where am I going to start and stop each of those terms? Okay, at the zeros, aren't I? Right, they're going to have to be at the zeros. So this is going to be an example. This is going to be a positive contribution. So I'm going to add that one up separately. This is going to be a negative contribution. And this is going to be a positive. Whoops. This is going to be a positive contribution. So I've got to break this thing right there and right there. This has to be one interval. This has to be another interval. This has to be another interval, right? I have to break those things where they cross the x-axis. Okay, make sense? So I have to add up the absolute values of the positive and the negative areas separately. So there's no cancellation going on. Okay, make sense? We're not going to do a lot with that this year, but you will. And it's an important concept in physics. Okay, so now another issue then. You'll get a little practice with that on the problem set. I think we better try one of those.
Yeah.
I think we better try one of those.
Yeah.
So I didn't have an example made up. It wouldn't be hard to do, but I'll see if there's. I can't remember if there's one in the book or not. If not, I'll just make one. Let's see. Oh, here we go. Okay, here's a good one. What about that guy? So let's say we want to add up, there's our position function. X as a function of time. We want to add up the total area, not the net area is easy.
Yeah.
If I want to add up the net area, what is it?
Just plug it in.
What's the net area? If I want to add up the displacement, what's the displacement? Displacement's simple because with displacement, we're going to let the math gods do their thing and just cancel positive and negative area, right? So what do? How do I add up the total? No, I don't want to say total. How do I add up the area under that curve, positive and negative alike? Okay, go ahead. You got. You know what to say. Say it.
You do the integral.
Okay, integral.
0 to 5.
Yeah, that's it. Integral of that. T cubed minus 6t squared plus 9t minus 2 from 0 to 5. That would be it, right? Okay, and we won't even do the integral. We could, right? I mean, that's how we would. I would agree that's how we would get the net area or the total displacement. I don't know. I'm not sure what it would be. There's going to be some. I think it has some. I think it crosses the x-axis internally there between 0 and 5. So there's going to be some negative parts and some positive areas that contribute, partially cancel.
0 should be -2, and then the positive 5 should be.
So could be. We could. We'll put it on our calculators to find out. But now, what if we want to find this is a little more difficult? What if we want to find the total area or the distance, maybe? What do we have to do first? We got to find the zeros. Yeah. Now we're not going to find the zeros here. Does anybody see? Does anybody know what one of the zeros are? Are there any of them that are easy to check? Like one. Does one work by chance? 1 minus 6. No, it doesn't, does it? 2. No. So we don't know what any of them are. We're not going to find this analytically. We're just going to cheat and use technology and find the zeros.
Hey, guys, so we do it.
Yeah.
Cheating is the best call.
Yes. Okay. So what's probably the easiest way to find the zeros using
Put it in the
technology?
calculator.
Okay. How?
Graph.
Graph it and find the x-intercepts, right?
No.
When he like seems like he's calculator, it's really cool on the back.
Car with the cat.
What's our function t cubed?
T cubed.
So of course we'll use x, right?
Yeah.
Our calculator's the variable it uses is x. X cubed minus 6x squared plus 9x minus 2. Okay, and all we'll do then is we'll just go to our window, right? What are we going to set the min at?
2.
Nope.
No.
0. Max? 5. And what I would do is I'd go zoom fit. Let the calculator fit the y-axis to the, then we'll tweak it if we need to. But zoom 0. It'll think for a second, and so it looks like we have lots of internal zeros to find, right? We got one there, there, and there. So we need to find those, okay? First one, so we would just go, what, second, calc, how do I find zeros? Duh. 0. Here's the number 2. Okay, left boundary. Now I can either, I'd say something else here that might be a little convenient to do. I'm just going to bail out of this. Let's go to our window. What'd they do? When I hit zoom fit, it changed the window from -2 to 18. Well, the 18 is unnecessary, right? We don't really need it to be 18. if you really want this to look a little better, let's go down and make that like -2 to +3 or something like that. How come? This might seem like a minor thing, and it sort of is. But then when I go to second calc and I choose 0, I can still see the x-axis while I'm working. Okay, why is that important? Not hugely, but I don't have to trace here. Tracing takes a lot of time. These are just minor things, but the more you know about this, the better prepared you are. You can use this thing in time college. I can type in values. Well, what would boundaries be that surround that first x-intercept? What numbers? Obviously, 0 and 1. So my left boundary I could pick as 0, enter. Right boundary I could pick as 1, enter. And for my guess, I could just go 0.5. And it gets me right to it. Okay. So one of them is, now these are decimal approximations. I mean, if we wanted, we're not going to take the time to go through this and do this another way, but I mean, that's good enough for now. So the first one would be, we'll call it x sub 1 is 0.26 out to 4 places, 8, 0. Actually, no, 7, 9. Okay, then we could do the same thing here. I could just go between like 1 and 2.5 and find that one. Let's go, we'll do it real quick. So we get 2, okay? Now, if we know, that's kind of convenient that one of those is an integer. Knowing that one of those is an integer, how could we find the other ones exactly? Think about that for a second. We'll come back and this is a good review. So we get 2, and then for the last one, we get, what? What are my boundaries going to be? 3 and 4? 3 and 4, there you go. Okay, so I should do that, shouldn't I? Okay, but I could do better than that. I lucked out and I got an integer 0. How could I take advantage of that and get these exactly instead of approximately? There's my original function. This is non-calculus stuff, but this is, okay, yeah, because think what we're doing here. This'll really pay attention to this, because this is stuff from previous years, but this is kind of stuff, these are kind of fun when you get these, oh, now I get it moments. What are we doing when we're finding a 0? All we're doing is we're asking the question, when is this, for what values of t is x equal to 0, right, is the vertical axis. Normally we would have said y versus x maybe, right? But now we got x versus t, right? So really all we're doing is we're just taking that original function and we're saying, whoops, not x, t cubed minus 6t squared plus 9t minus 2 equals 0, right? And these are the places where it happens. But this is nice. One of those is an integer, right? Now, how do we normally find zeros of polynomial functions? What's our strategy? Factor, right? So if 2 is a 0, what is the corresponding factor that would go with that? T equals 2 is a 0. When I have this thing factored, right, if I have this thing in factored form, what's the one that goes there if the solution is t equals 2? The solution of what 0, if I said it equals a 0 itself? T minus 2, right? Remember that?
Oh.
Does that make sense? Okay, so we know that one factor, And that's a really important connection to make, that if we know a zero, you know, same thing as an x-intercept or a t-intercept in this case, it also tells us a factor, doesn't it? It tells us a factor, that is a factor with no remainder. That one divides perfectly into, t minus 2 divides evenly into that polynomial. What's left over? Let's just call it, for now, let's just call it r of t, or whatever's left, right? How would I find that? Really, really easily. Yeah, I could divide, if I just divided this by t minus 2, that would tell me what's the other factor is, wouldn't it? That's a linear factor, and so I can divide that really quickly and easily, right?
Yeah.
How do I do that? Remind me.
Do box. Yeah. area.
Synthetic division,
Yeah,
right?
That's
Okay.
what it is.
What's my remainder guaranteed to be in this case?
Zero.
It has to be 0 because that is a factor. It divides evenly. Okay, what goes up here?
1 or -6.
Okay, the coefficients in order, including 0 coefficients. There aren't any here. But if I were missing a power of t, that would constitute a 0 coefficient, right? So I've got to have 4 of them here. That's going to be a -2, that's a 9, that's a -6, and that's a 1. And what goes out front? 2, right? The 0 of this factor goes out front. And now I just do my synthetic thing, right? So I bring this guy down, remember? So that's a 1. Whenever a number appears at the bottom, I multiply and add diagonally, right? So 1 times 2 is 2. Add vertically, sorry. So then I get -4. 2 times -4 is -8, so that's +1. And then, of course, 2 times 1 is 2, and those have to add to 0. That's how I can check it. So what does this tell me?
X.
That's what it is.
Yeah, good. Good, coefficients, but t's, not x's, right? Those are the coefficients of the factor. So we're gonna get 1 t squared minus 4t plus 1, right? So here, we could have replaced that with, what was it again?
T squared minus 4t plus what?
T squared minus 4t plus 1. And if I wanted to find the exact zeros of that factor, the other two zeros, what would I do? Well, I probably can't factor any further,
Split.
but it's quadratic. Quadratic formula, right? Once I get it down to I can find the zeros of any factor that is quadratic or less. If it's less, it's simple. That's just solving a linear equation. But if it's quadratic, I can always rely on the quadratic formula, right? And really, at this point, it's not going to factor, is it? At this point, this is really just telling me A, B, and C, isn't it, for the quadratic formula?
Yeah.
So we could do that. And I would get both of my answers in terms of square roots, so they would be exact. Everybody see that? I'm not going to do it. We don't need, you guys can all do that. But you get the idea, right? Okay? So then on my calculator here, when we go back and look at this graph, all I would have to do is break this up into 3 separate integrals, wouldn't I? Right? Everybody see that? And I'm going to take the absolute value of each one. Now I want to write that out though, because that's kind of a big deal. So I'm going to get rid of all this stuff we just built. That's what we could do if we wanted to. It's nice to know that we could. So if I wanted to get the total area, I would take the integral of that, right? From where? 0 to,
What?
no, if I'm adding, I don't want to add up net area.
0.2679.
Oh.
There's the first 0, okay?
Oh.
Okay, and I have to do absolute value of that, right?
Yeah.
Because I've got to add that up as a positive contribution. Plus absolute value of what? integral of, I'm just gonna call it x of t. Right, it's just that. From where to where? 0.2679 up to 2, right? Then plus, same thing, absolute value of the area from 2 to 3.7321, plus
That.
that to 5. I gotta break it into 4 parts, don't I?
Well,
Right?
no, thank you.
Right, well, I mean, you're gonna have to do that. And here, we can see the contributions. That's gonna be a negative contribution from the first part, positive from the second, negative from the third, positive from the fourth. And if I add up that area, I could even do this. I could do this on my calculator, but I'd have to it'd take a little extra work. I mean, right, I'd have to just add these up separately and take absolute values of those, right? Okay? Questions on that? Does that make sense? Okay? Next issue. Okay, let's go back and look at our picture again. Okay, this time I just want to know what's the average velocity? The average velocity in this case is pretty simple, isn't it? Right, like let's get rid of, how about if we get rid of this guy for the moment? Kenny's not there. Average velocity for a constant is pretty simple, right? It's just going to be 6, right? Okay, what if, though, we have something like this where, let's say this guy, let's say we travel at 4 for 8 seconds, 4 meters per second for 8 seconds, and then we travel at 8 meters per second for 8 seconds. So I've broken this up into 2 parts. Now what's my average going to be? I could just add up the areas, and, couldn't I? And divide, right? I mean, I could add up the areas and divide by the total, couldn't I? What's the area of this rectangle? 24. Okay, so 24 meters is that area. What's the area of this one? 64. And this took a total of 16 seconds. From there to there is 16 seconds, right? And so isn't really the definition of average velocity physics types, it's just total displacement divided by total time, isn't it? Right? So the total displacement would just be 24 plus 64, what, 88? Divided by 16? Oh, is that right?
Wouldn't the 24 be 32? Yeah.
That should be 32. Yeah, that's not right. Right, so we get 32 plus 64 is 96. Okay, divided by 2 is what?
Yeah.
Or divided by 16 is what? 6.
Yes.
You know, that makes sense, doesn't it? Now think about that. That really does make sense because I could create the same area from an easier shape. How could I do that? How could I kind of cut and paste and make that look? Oh, yeah. What if I did this? What if I just took this top piece off? Let's say I cut this guy right across here like so, and I take this piece right here and I pivot it so it fills in right there. Right? Isn't that, I mean, by doing that, aren't I just doing this? I'm adding a little bit of extra to this one and I'm taking that extra away from this guy and creating that shape.
Yeah.
Right? Have I changed the area under the curve?
No.
No, I haven't. Right? All I've done is I've just redistributed the area a little bit. But if our question is only what's the average speed, average velocity, why not use cruise control instead of going slow for a while and then going fast? Cover the same distance, right? Okay, now what happens though, if I go back a little bit. Okay, let's say that this piece right here is going to be over a much shorter period of time. what's that gonna do to my average then? If I'm traveling at 4 meters per second for only 2 seconds, and I'm traveling at 8 meters per second for 14 seconds, what's that gonna do to the distance that I cover? It's gonna go up quite a bit, but I could play the same trick, couldn't I? I could drop this one down very slightly and add that area to this guy and they would, right, does that make sense? Okay, but it's starting to get more complicated now, right? It's getting a little more complicated. And it even gets much more complicated than this if, well, let's say we do something like, this still isn't much more complicated, but it's a little bit. What if this guy, oh, can I not do that? I bet I can't. No, I can't. So let's do. I can't, it's no big deal. I didn't work it out. Never mind. I don't mess with it. So what if I just do this? What if I have something like that? That's my area. Right. It gets a little more complicated. This situation is where I'm starting at rest and it's just constant acceleration, isn't it? But once again, I could tell the same story if I just cut this top piece off and pivoted that around. And instead of starting at rest and accelerating the whole time, if I just had been driving and I crossed the starting line with my cruise control on, I'm still going to cover the same distance, right? Okay. Still, we could probably manage that without calculus. We could, right? I mean, we could just do this all geometrically. But I double dog dare you to do this one without calculus. What if we start here and we go like that? If I want to find the average, the mean value of that function on that interval, now that's pretty hard to do geometrically. What would I have to do? Well, okay, yeah, but we're past that, right? If I want to find, we're going from, and I'll even make this even tougher. Let's say we're going to start right here. We're going to add up from A to B. We want to know the average, the mean value of that function. What am I going to do? Same thing we did earlier, right? Average, mean value, same thing as our previous example. We had average velocity, just total displacement divided by total time, right? So isn't the average value or the mean value of that function just the total area divided by the width? Everybody see that? I could. It's a little more complicated this time. I have to bring in some specialized instruments. But if I had a two-dimensional grinder, I could come in here and grind this thing down from the top. Bring my two-dimensional grinder in and create some two-dimensional rubble. And as the rubble trickles down along the sides, as I'm plating off the top of this thing, I'm going to get to a point where, Brian's looking at me like I'm crazy here. If I, oops.
Well, you know, you are kind of crazy.
Yeah. I'm going to eventually get to a point where when I plane off all that stuff up there, right, and the rubble I create is just going to trickle down and fill in these gaps. Eventually, I'm going to get to a point where I could redistribute that two-dimensional area into a rectangle. Right? Does that make sense?
So now we have Caterpillar tractors too.
That's right. Two-dimensional
John
planes.
Deere.
They have no thickness. They only have 2 dimensions.
All right, that's fine.
So we're bringing, right? You see what I'm getting at? If we just push the top down and redistribute that area, I could take this blobby-looking area and turn it into a nice, convenient rectangle.
I can do the tractor part, I just can't do that part right there.
So the height of that rectangle is significant how? It would be the average velocity if we're talking about velocity versus time. it's the mean value of the function if we're just talking about something random. Maybe it's not position in time, maybe it's just f of x and x, right? In other words, the blue area, which we can write this way, the integral of f of x dx from a to b is just this area right here, isn't it? Right? Has to be equal to, the purple area would just be this value right here, which is the mean value of the function. Okay, for now, we're just gonna call that f of c, that's the mean value, times, how wide is that interval? A to b, so what is that with it? B minus a. How about that? Isn't that cool? Okay. We'll finish that up next time and we'll be done with everything.